Well, welcome to our Turbulence Tea gathering, which has been happening over the past 2 times over Zoom. So I'm very pleased to introduce you to our speaker today, Javier Urzay. Javier, as all of you know, is a senior research associate and engineer at the Center for Turbulence Research for nearly a decade, apparently. In March will be 10 years. And he has been interested all along in reacting flows and mostly with application to rockets, internal and propulsion devices, two-phase flow, combustion, hypersonics, aerothermodynamics. Many of these areas he has been interested in and has been active in doing research in these areas. He is our resident rocket scientist, and over the past couple of years, I think, or maybe more, he and Louis Jofre were working on this area that he's going to talk about today, which resulted in a big paper that I think almost like a book that they submitted to a journal, and I think Javier is going to at least talk about in this short presentation, talk about the surface aspect of it, if you will, touching the surface on it, and which is quite appropriate for the CTR Tea Seminar. So thank you, Javier, for agreeing to put this together, and I'll let you start your seminar.
So let me just say here something about the motivations. And most likely I'm going to spend most of my talk in this section, so I'm not going to move away from this section too much in this talk. So, for instance, I think we know from our classes, right, of chemical thermodynamics when we were undergraduates, that if we have here a pure substance, let's say, right, for a pure for a monocomponent system. Monocomponent system, right? So I can plot here an axis and here another one, right? And look at the thermodynamic phase diagram of this single component. So this is going to be temperature and this is going to be pressure. So I think we all remember that here there is a line, right? So there is a line that does something like this, that separates liquid from gas, right? And this line here is typically called the vapor-liquid equilibrium line. So I'm going to call it vapor-liquid equilibrium line, right? And it's a line that indicates phase equilibrium and can be calculated with the Clausius-Clapeyron relation, right? And we did that when we were undergraduates. So if I take a system here, right, I have this thermodynamic state there on top of that line. The thermodynamic state is going to be in phase equilibrium. That means that the liquid is going to be in phase equilibrium with its own vapor, right? And if I look at an experimental image of the system in this thermodynamic state, I'm going to see what you're going to see on the slide. So you're going to see a system, right, that is separated in between liquid and gas, right, like that equilibrium cell that you have in the slide, with gas on top and liquid at the bottom, and they are separated by an interface. And that interface, by the way, is small, right? It's actually very thin, and it can be like 1 or 2 molecules of thickness, because the gas at low pressures, at atmospheric pressures, is not subjected to any intermolecular forces, whereas the liquid actually has very strong intermolecular forces. So that interface is very thin, and actually, as you know, that causes problems in numerical simulations. So, well, So if I look at this plot here, right, and I try to plot this diagram instead of this axis, I try to plot it, right, in terms of a third axis here that could be the third thermodynamic variable, for instance, the molar volume. Then this plot is going to look like this. So I'm going to have here the molar volume, right, and here I'm going to have the pressure. And this line that you have here, right, this vapor-liquid equilibrium line is going to be transformed into a surface on this diagram. So on this surface, it's going to look like this. It's going to look like a bell-shaped curve with this surface here, right, inside, that is called the coexistence region. You could call it the two-phase region, right? I'm going to call it the coexistence region. So again, this is the vapor-liquid equilibrium line. So here I'm going to have liquid, here I'm going to have gas. And in particular, if I go very much here to the right, I will have an ideal gas. So if I take the system, for instance, at constant pressure, right, as is typically the case, as in that experimental image, so a constant pressure, say at atmospheric pressure. So an isobar here is going to intersect the vapor-liquid equilibrium line at these 2 points, right? And at those 2 points, I can read the molar volume, so there and here, and this is going to be the molar volume in equilibrium corresponding to the gas, and this is going to be the molar volume in equilibrium corresponding to the liquid. So in other words, at a given pressure, I have 2 solutions of the problem. So it is important to notice that at sufficiently low pressures, these 2 molar volumes are actually the rendered densities that are very much different. So in other words, the density in equilibrium of the liquid phase divided by the density in equilibrium of the gas phase is actually very, very large, and it tends to be of the order of 1000. And that's typical, right, of low pressure fluids in phase equilibrium. So this density ratio is of order 1000. That is what you would have, for instance, in an atomizer of operating at atmospheric pressure. So, well, it is important here to notice, right, that as I start here increasing the pressure, then the problem changes fundamentally, right? So this is something that we know already at atmospheric pressure, but if I start changing the pressure, right, in particular I approach here a point that appears that is called the critical point, then the solution of the problem is going to change, right? And we know that already. Just let me tell you here that this defines here a critical temperature and a critical pressure. And just to give you, for instance, an example for nitrogen, right? For nitrogen, I will have for critical temperature is going to be 126 kelvins, and the critical pressure is going to be 34 bar. So this critical pressure in this diagram, for instance, will be visualized here, the point up there, right? That is going to define the critical pressure, and an isotherm, that is going to be the critical isotherm, that is going to be tangent to that point. So if I go above, if I start increasing the pressure here, I'm going to hit this region, right? But notice that I'm not bounding here by any straight line or anything like that, because it is difficult to bound it correctly. But up here, the fluid is going to be supercritical. So up here, I'm going to have a supercritical fluid. Up here, to have supercritical. And here, there is no more any clear distinction between liquid and gas, right? One of the things that you're going to see, you're going to realize is that if I evaluate the system here at a given, for instance, molar volume, or at a given pressure, there is only one point. There is only one solution at a given pressure. There is only one temperature, one pressure, and one molar volume. And that already tells you that I don't have the bifurcation that I have here, in which I had 2 well-defined molar volumes. So I only have one now. And that one is the molar volume of the supercritical fluid, right? And I can see that, for instance, in the experiments, as one increases the pressure, then the interface disappears, right? Then you see that the interface disappears as one goes above the critical pressure. Well, this is something that is well known, right, in the literature. Now you may be wondering, well, so then what is the interest of all of this? Why are you even talking about this? Well, I'm not going to tell you yet why am I talking about this, but I'm going to tell you something else, right? And it is that even though there is no clear distinction here between gas and liquid, there is a line that typically emanates from the critical point, this green line that I'm plotting there, and here this other green line, that is called the pseudo-boiling or Witham line, right? So the green color here, I'm going to put, it's called the Witham line, right? And this Witham line is characterized by the maximum of the specific heat. So the specific heat actually attains a maximum there, and it's a finite maximum, so that means that you have sort of a second order phase transitioning happening here. And in particular to the left of this pseudo-boiling line, right, you have something that resembles a liquid, and you can see that this is sort of a remnant, right, of what is happening below the critical point. So here you have something that resembles a liquid, but it's like liquid-like, right? I don't say liquid, but it's liquid-like. And here on the right, there is something that resembles this gas, and it's gas-like, right? So here we have gas-like, right? And there is a strong difference, not as strong as down here, but there is some difference between these two types of fluid. So for instance, if I look at the temperature, right, so this is the temperature axis, and let's say that here I have a pseudo-boiling temperature at a given pressure. This pseudo-boiling temperature close to the critical point is actually very similar to the critical temperature, right, because it emanates from the critical point. So well, here to the left of the critical temperature, I'm going to have something that resembles a liquid-like, right? Whereas here to the right, I'm going to have something that resembles a gas, so that means gas-like. So for instance, if I plot here the isothermal compressibility, right, so I know that the liquid is going to be almost not compressible. It's going to be almost incompressible, right? So if I plot here the isothermal compressibility is going to do something like this. Isothermal compressibility, by the way, is this. It's the variations, the percentual variations of the volume with respect to the pressure at constant temperature. Now, if I plot, for instance, here the density, well, I know that the density of the liquid is going to be much larger than the density of the gas, but not as large as before. But still, I'm going to have some change in the density. So that will be the density. Now here, this density jump is no longer 1000, but it tends to be of order 10. So the density jump tends to be of order 10, like 5, 40, things like that, right? So if I plot, for instance, here the viscosity, well, the viscosity is going to behave on the liquid-like, is going to decrease with temperature as in every liquid, right? So the viscosity is going to do something like this, and then for the gas is going to actually increase with temperature. So this will be the case for the viscosity and the thermal conductivity. And if I plot, for instance, the mass diffusivity, I'm not running out of colors here, but say that the mass diffusivity is going to do something like this. It's going to stay mostly constant on the liquid side, and then it's going to increase with temperature on the gas side. So those will be the differences between liquid-like and gas-like. Remember, these are just single component systems, right? So if one looks at this system, right, then you may say, oh my God, so I have here some changes in the properties around the pseudo-boiling temperature. It is true, right? So for instance, let's imagine the case that I go here and I try to run this experiment. I have nitrogen injected at a temperature of 105 kelvins. And then here I have a chamber, and the chamber has a temperature of 300 kelvins. Well, if you remember, right, I gave you here the critical temperature of nitrogen. So if, for instance, if I evaluate this system at 50 bars, the trajectory of this system somehow is going to cross this pseudo-boiling line. Somehow it's going to cross it, right? And it is true that you will have these gradients there. You will have gradients that are relatively large around the pseudo-boiling temperature, but those gradients are actually delocalized in space. Even though they look like they are localized, they are much more delocalized than in the case of an interface. they are much more delocalized than in the case of an interface. And in fact, in this system, it is impossible to develop an interface. So you can see the result of what is going to happen in experiments. Here I'm showing you the same diagram calculated with the Penn-Robinson equation of state, so you can see the different lines that I was sketching. And here you have experiments, right? So on the first panel on the left is at subcritical pressures, right? So subcritical pressures, you have here nitrogen injected into nitrogen. So the temperature of the nitrogen is 105 kelvins and the ambient is at 300 kelvins, as I was saying. So at subcritical pressures, you have a spray, like the everyday spray, because the system is subcritical and therefore there is an interface. As you approach the critical pressure and you surpass the critical pressure, then one starts seeing that there are no droplets anymore, right? So as I told you, the system is, for a given pressure and a given temperature, the system is single valued. So you cannot develop an interface anymore. So what you see is mixing, even though the system has some gradients there because of its changing properties across the pseudo-boiling line, but there are no interfaces. Well, so sometimes this behavior right here has been associated with transcriticality, right? But I'll tell you that this is not the transcriticality that this paper is about. So you now see that I have spent 20 minutes explaining what I'm not pursuing, but it is important to clarify what I'm not pursuing in this talk before telling you what I'm pursuing. So, well, before moving further, let me just go back again here, right? I'm explaining something that is very fundamental. So what happens if instead of going supercritical, I actually go back to subcritical, right? Because I need you to see something. So if I go back to subcritical, right, and now I'm here inside this coexistence region, then the system develops an interface. As I approach the critical point, that interface becomes thicker and thicker and thicker, and at some point disappears. It is important to notice that as the system approaches the critical point, the interface actually becomes diffuse, right? And by diffuse, what I mean is that the system enters in the continuum. Sorry, the interface enters in the continuum, right? And it enters in the continuum because the mean free path is inversely proportional to the pressure. So the Knudsen number associated with the interface actually decreases with pressure, and the interface starts entering in the continuum. And Van der Waals actually realized of that 130 years ago. He realized of that, and he created a very useful theory to treat monocomponent isothermal systems. Those are the easiest systems that you could imagine, monocomponent and no temperature gradients. Then he realized of that, and he formulated a theory to treat the interface close to the critical point, right? Well, I'm not going to tell you the details of the diffuse interface because I promised myself I wouldn't write any equations here. But what I'm going to do is to tell you what is the idea here, right? What is the core of the idea here, what Van der Waals developed. So Van der Waals realized, he was very smart, he realized of the following. If you take a point here inside the coexistence region, we are tempted here to calculate the concentration of vapor and the concentration of liquid as we did when we were undergraduates, right? With a lever rule and things like that. But then he realized, he said, a system that is there, most likely what is going to happen is not going to be homogeneous. In other words, you're going to have liquid on one side, gas on the other side, and I cannot treat the system as a homogeneous system filled with liquid and vapor, right? So somehow the two phases, they need to separate. So he created a theory to separate the phases. If we go here, right, to this problem that is supercritical, right, that is fully supercritical, I could simulate those experiments, those supercritical experiments, by using a high pressure equation of state. For instance, the Penn-Robinson equation of state. Or any equivalent equation. Right? This together with high transport properties, I could simulate that experiment that I just showed you that it doesn't render any droplets. I could simulate, and people, they have done that before, right? Now, the problem is that when the system separates in phases, right, then this formulation is not going to work. is not going to work, because van der Waals realized that in his equation that had his name, with this cancel and this cancel, that was the van der Waals equation, this parameter here that describes the attraction forces between the molecules when the pressure is high, that parameter there is not enough to separate. It's not enough for separating the phases. So in other words, this equation of a state by itself is never going to separate any phases in the flow. So what van der Waals realized is that there is another parameter that is required here, and it comes from the non-locality of the thermodynamic potentials. In other words, he went back and he rederived the thermodynamic potentials in the presence of a density gradient across the interface, in the presence of a strong density gradient. And then he realized that, for instance, the Helmholtz free energy can be written in terms of a local Helmholtz free energy plus 1/2 rho multiplied by a coefficient and multiplied by the square of the gradient of density across the interface, right? So this is n hat. So he realized, he said, well, by using derivations that I don't have time to talk about here, he said, well, the thermodynamic potential no longer depends on the thermodynamic variables themselves, but it also depends on the gradients, right? On the gradients. So this is a long-range effect in the thermodynamic potentials. And this coefficient that is here is called the gradient energy coefficient. That deserves another separate talk. But we'll just tell you, right, that this coefficient is typically adjusted using experiments, although it has a meaning in the molecular structure of fluids, although it seems to me that that hasn't been exploited yet, right? For instance, for multi-scale simulations calculating this kappa on the fly, right, using molecular dynamics or something like that. So he realized of this, and then if you rederive the conservation equations for a monocomponent isothermal system, he realized of the following. So if I plot here the coordinate normal to the interface, and here the density, right? The density is going to do something like this. So you're actually going to have a strong gradient there. Strong gradient, right? This is the interface. Well, so what van der Waals did was the following. Look, so hope we can capture this, right? So this is the diagram that I was showing you before in the slide, right? And you see that it has there here. You see that it has there an oscillation in the pressure, right? That's called a Maxwell loop, and that's an isotherm. So if this interface separates two fluids in equilibrium and the temperature is constant, the trajectory is going to be the green trajectory in pressure and in molar volume, right? So what, let's go here, what van der Waals did was the following. He said, okay, there is an oscillation of the pressure as a function of the density in that plot that I just showed you. So by a transformation that comes from theoretical considerations, he was capable of mapping the density in a space, right, as this type of function that is very steep, in such a way that this diagram here, this thermodynamic diagram, right, I can fold it now. I'm going to fold it like this. This diagram now comes here. Look, it's folded there. It's folded within the interface. So all the thermodynamic phase diagram is coded actually within the interface, and it's folded there because there is a third coordinate here, which could be another thermodynamic variable, right? So it's actually folded there, and it's beautiful. When one realizes of that, it's actually very beautiful theory. So, okay. So now let's go back here, right? One thing that van der Waals was capable of doing is actually calculating the surface tension. So the surface tension in his theory is actually given by the integral from -infinity to +infinity of kappa multiplied by the gradient square of the density. Right, see, he was capable of calculating this surface tension. Well, it's interesting to notice too that the internal structure of the interface, is fundamental for setting mechanical parameters like the surface tension. So in other words, I cannot have any arbitrary internal structure of the interface, because then that would render the wrong surface tension, right? Well, so when one uses his theory and compares it with experiments, then you will see this plot that you see here. So here, what I'm plotting is the reduced temperature and the surface tension, and you see that the surface tension actually goes to 0 at the critical point, right? It goes to 0 at the critical point. So the surface tension vanishes above the critical point, as I was mentioning before. So these are results of van der Waals theory, which are equivalent to our theory when we simplify all what we have done to the case of monocomponent and isothermal systems. All right? Okay, so then you may be wondering, but Javier, you know, the problem actually looks easier, because if you go above the critical pressure, then there are no interfaces. So who cares about this, right? So who cares? So it looks like the problem is actually easier than when the system is subcritical. Well, so here's the core question in transcritical flows, right? The core question that I'm capable of formulating at this point is that there are systems that are multi-component, right? Such that each one of the components are above the critical point. The conditions are above of the critical point for every component, and you still see interfaces. You know, and that blows my mind. And actually, that was the beginning of everything. So, why is that happening, right? Why is that happening? Well, in order to understand that, one needs to study systems that are more realistic than this. So that is to say, systems that are of relevance for propulsion, and those are typically bicomponent or multi-component systems, right? So let's talk about propulsion now. So let me talk here about gas turbines or jet engines first. So if I look at a gas turbine, right, or at a jet engine, right, so I have a compressor here, right, I have a turbine here, right, I have the exhaust there, and then, you know, this is the fairing of the engine. So I'm ingesting here flow at nearly atmospheric pressure, because the Mach number is small, right? So the pressure, the static pressure there is going to be the atmospheric pressure. And here I have the combustor, right? And the combustor is, here I'm generating pressure. So here the pressure P infinity of the combustor is going to be high. In particular, this force, this thrust force, is actually proportional to the pressure. So the more pressure I have, the more thrust I'm going to have in the engine. So the compressor is going to elevate the pressure, right? So it's going to go from PA and P infinity. And there is a particular number that is used in characterizing jet engines, and it's called the overall pressure ratio, right? This is equal to P infinity divided by P sub A. So in modern jet engines, this overall pressure ratio is of the order of 40 to 60, and keeps on increasing. So this is to say that when here I have 1 bar, so that is to say the airplane is on the tarmac, then here I'm going to have a pressure in the combustor pressure, which is going to be 40 to 60 bars. And this overall pressure ratio keeps on increasing, because the higher the overall pressure ratio, the smaller are going to be the emissions of CO2, CO, and burnt hydrocarbons. So let's see this in a slide. So this is year, right, versus overall pressure ratio for modern jet engines, actually dating back to 1960 till 2020. So you see that the modern engines actually, they have a very high overall pressure ratio. So I'm also there plotting the or indicating the critical pressure of air and the critical pressure of jet A, right? So just to give you here some numbers, right, for air, the temperature, the critical temperature is 131 kelvins, the critical pressure is 34 bars, and for jet A, the critical temperature is about 671 kelvins, and the critical pressure is 22 bars. So there is a point, as you saw there in the screen, actually, that the modern engines, they actually operate above the critical pressure of air on the tarmac. So if I look at the combustor here, right, this combustor looks like the following. I have here a jet of fuel, right? I mean, There are geometrical details here that I'm not taking into account, but let's say that here you have a fuel. So this is going to be at some temperature. Here you're going to have a co-flow of oxidizer, which in this case is air. Also at another temperature, T sub O. Here you going to have the combustor, and you have a flame and all of that, right? So the pressure here at takeoff is going to be the order of 40 to 60 bars. Well, the injection temperature for the fuel needs to be near ambient because the fuel cannot be preheated. This is a hydrocarbon fuel and it cannot be preheated because if it is preheated, then it's going to generate deposits. It's called cooking, right? So it cannot be too hot, so it's going to be like that. And then the temperature of the air stream is going to come from the it's going to come from the compressor, and this is going to be the order of 700 to 1000 kelvins. So this would be the typical, scenario that I would have in a gas turbine engine. And if we look at the slide also, that means that the modern engines that are actually injecting supercritical liquid-like fuel into supercritical gas-like air. Right? So this air stream looks like a supercritical gas-like fluid, and this looks like a supercritical liquid-like fluid. Right? Okay, so those are typical transcritical conditions. The same happens, actually, when I look at this thing, right, with this pressure, this looks like very much like a rocket, right? It looks like a rocket to me. So, for instance, if I look at a rocket engine, what I have is a combustor attached to a nozzle, convergent divergent nozzle. Right, so this combustor is going to be again ingesting fuel and oxidizer. So I'm going to have some pressure here in the combustor. So here I have a supersonic flow, the nozzle is choked, and therefore as a result I'm supposed to have high pressures here in the combustor. So the combustor, as I said, is going to be fed by fuel and by oxidizer. Well, so I could take, for instance, the fuel, right, and inject it directly into the combustor, and then the oxygen and inject it directly in the combustor. I just wanted to let you know that, for instance, the oxidizer tends to be liquid oxygen, and the tank of the oxidizer typically is at 5 to 10 bars. So it's cryogenic, but it's still subcritical, right? Subcritical cryogenic. Whereas the fuel, right, if for instance I pick rocket propulsion fuel, it's a heavy hydrocarbon and it's going to be stored at 300 kelvins and also 5 to 10 bars. Still subcritical. So I cannot take the fuel and inject it here and the oxidizer and inject it here. That is what we are doing in PSAP 3, but that does not generate thrust, right? So what typically we do is to put here a pump. Here you put another pump, and then you generate here a sort of a turbo pump, right, with a turbine in the middle. And then what you do is to pass the oxidizer, right? You pump the oxidizer, you pump the fuel. So it should be in this direction, right? You pump the fuel, you pump the oxidizer. And then what you do in order to move the pumps is to have a pre-burner. Right, so you have a pre-burner here, and in that pre-burner what you do is to inject the oxidizer, right, and you inject also the fuel, and then you burn them, right, and in this case, this particular design, you burn it in oxidizer rich conditions. Then you take the burn gases, right, here, you pass them through the turbine, the turbine moves the pumps, right? And then you take the result, I'm going to take it over here, and then you send it to the combustor. So here you take the fuel, right? Part of this fuel, you pass it through through the nozzle and through the chamber, and then you inject it there. I could tell you, for those of you that you do wall modeling, I could tell you some fundamental problem that arises here near the throat that is related to the curvature of the throat in this cooling channel. So if you are interested, just feel free to ask a question during the questions time. So here, right, this pre-burner, right, this pre-burner that you see here, this pre-burner has pressures that are of the order of 300 to 560 bars. And this thrust chamber, the main thrust chamber, develops pressures that are of the order of 200 to 300 bars. Those are very high pressures, all right? And those pressures actually, they are increasing with time. So if I look at this chart, right, as the time goes by, actually the pressures are actually increasing. And you see there the pressures of Raptor and BE4 that are actually very high. So this particular design that we have here actually was used in the RD-170 in the Energia project for launching the Buran in the Soviet Union, and it is also used today in the BE4 of Blue Origin, although Blue Origin is using here methane instead of RP1. Well, if I look at the temperatures, right, if I look at this combustor, the main point that I wanted to do here, to make here is the following. If I look at the combustor, in this combustor I have, again, omitting the geometrical details, I have some fuel here injected. I have a co-flow of oxidizer. So this fuel is going to be injected after cooling the chamber and the oxidizer, and the temperatures are going to be of the order of 300 to 450 kelvins. And this is a hydrocarbon, right? And then the oxidizer is going to be injected, right, after passing through the pre-burner. After passing through the pre-burner, the oxidizer is actually hot, so this is going to be injected at 700 to 1000 kelvins. And the pressures here, again, are going to be like the order of 300 bars. So when you look at these two sketches, you say, oh my God, look, they look the same. They look very much the same, right? This one looks very much like this one. So that's why we say that these days jet engines, they actually develop pressures that are very similar to rocket engines. These two actually they are pretty similar, and both are transcritical conditions. So you may say, why are they transcritical conditions? Because of the following. If I take this similar setup, right, and instead of using rocket propellant, I use Jet A. Sorry, instead of using rocket propellant or Jet A, I use dodecane. Then I will see this, which was seen in experiments. So there you have a system that resembles the one that I have plotted on the whiteboard, right? And you see that the fuel is injected in a liquid-like form, and the air, or the ambient air here, this is actually nitrogen, is in gas-like form, right? And the pressure is supercritical with respect to both components. And then you see there a spray, right? You see a spray happening there, right? Which is actually interesting. So if I look also at the surface tension in terms of the pressure for pentane and decane, there is actually surface tension at very high pressures above the critical points of the two components. So what is going on here, right? What is going on? So this is actually the question that we answer in that paper. This is actually the question that we answer in that paper. So, well, I'm not going to tell you very much what we did in that paper, but just to give you some superficial explanation here, we actually reformulated the Navier-Stokes equations using an extended version of the van der Waals theory, extended to multi-component and non-isothermal systems, right? And that entails modifying the stress tensor to incorporate an interfacial stress tensor. It entails also modifying the diffusion flux to incorporate an interfacial species flux, and the same for the heat flux. And the derivation of those terms is complex, right? And it is detailed in the paper. All right, so let me just finish here, right? I'm just going to spend another 5 minutes just giving you what the theory gives. This is a sketch of the solution. In the paper, you're going to find, more quantitative explanations of this structure. But this is the fundamental structure that arises from the theory. that we calculated actually numerically. So here you have exactly the same configuration that I was telling you on the whiteboard, right? Exactly the same configuration, so gas-like, hot, supercritical, co-flow. And then a core of liquid-like, supercritical heavy hydrocarbon fuel. You need to understand too that we focused on heavy hydrocarbons because heavy hydrocarbons, they have very high critical temperatures, right? And that's essential for these transcritical structures to survive, right? Because if the temperature, the critical temperature is high, then it is going to take some time. It's going to take some distance to actually heat up the fuel stream to its critical temperature and then make the interface to vanish. That's the first point, is that transcritical conditions are exacerbated when there is a heavy hydrocarbon fuel being used. Right? And the second thing that one is to take into account is that even if the critical temperature is high for heavy hydrocarbon fuels, that does not imply that there is going to be an interface by itself. So the presence of the interface has to do with a telescopic effect that happens in the critical point. So when you take two elements, two species, and you combine them, then the critical point actually rises up, right? So actually the pressure increases. And you can see here in this plot, right? So here I'm plotting, this is a three-dimensional phase diagram, right? For dodecane nitrogen. And you see both pure components, right? The critical points of both pure components there. And you see that the coexistence region actually has this promontory, right? And that promontory actually reaches up to 1,000 bars. So you can have actually systems, dodecane nitrogen, dodecane air, dodecane oxygen, and many other hydrocarbon air mixtures that whose coexistence region actually reaches up to thousands of bars, right? So it is when the system is supercritical with respect to both components that then has a chance to traverse that promontory, and going through that promontory means necessarily that there is an interface, right? So the interface is generated by the formulation that we developed in that paper, and it has an apparatus behind, right, that it is related to the separation of phases. So there is a point in which the phase becomes diffusionally unstable, right? And then you need to have a transport theory that is capable of separating both fluids when it traverses the diffusionally unstable part of the thermodynamic phase diagram. Here, again, I have not explained what a diffusionally unstable mixture is, so I can only tell you very superficial comments about this. I will just show you one plot, right, that is the structure of that edge and can be calculated numerically, and is this edge that you have here. That to date I have not seen this structure reported other than in our paper. So this is a fundamental structure that can be calculated with this theory, and it gives you something that is called an interface edge, right? That in which the interface terminates at the diffusional critical point. So there you have an interface upstream of a diffusional critical point, and there are supercritical mixing layer downstream. Should also say before finishing that there are other configurations that one can have that are not strictly related to an interface vanishing, but it could be a spray, right? If the liquid has already broken up, it could be a spray, and then the critical conditions that are given by the critical diffusional temperature could penetrate the spray cloud and supercriticalize the spray cloud instead of supercriticalizing the interfaces in this case. So here is the decay of surface tension that one can calculate, right? So the surface tension survives for some distance that is equivalent to a thermal entrance length that one can also estimate with this theory. So I'm going to finish here, right? And I'm just going to leave you here with this summary of capabilities of the theory, and I'll be open to questions if you have any. Thank you very much.